Morning and welcome to section 14.5, which we're going to talk about the chain rule. And we're going to talk about the chain rule when we're differentiating functions where we have more than one variable, especially in Calculus 3, where a lot of the properties that we did for chain rule in Calc 1 are going to be the same properties that we're going to do for Calculus 3. But again, we're going to have more variables this time. So I'm going to show you kind of what we did in Calculus 1 and Calculus 2 and show you how it's really not different, even though it appears to be different. When we're talking about doing the chain rule, what we did was we had composite functions. We had some function, and inside that function was another function. All right, and usually we saw it this way. We saw it as y is equal to, let's say, 3x to the fourth. All right, and we wanted to take the derivative of that. If we decide to take the derivative of that, we would, take the derivative outside times the derivative of the inside. Right. Another way of looking at this is saying, okay, well, let's make the inside defined by something. I'm going to define it by t. Usually we do u substitution, so I'm going to go ahead and define the inside by t. So I say t is equal to 3x, and so then my equation y would be t to the fourth. And so I guess I should have used u. It doesn't matter here. So what I can do is, and this is what the chain rule is, I can take this function here and this function here, and here you see it's a composite, and I can say, well, if I take the derivative of, because I really want the derivative of x, take the derivative, and since I'm not doing partials right now, take the derivative of y, but I want to find, I really want to find the derivative over here, right? I can take the derivative of the 2 that we have boxed up and say, okay, well, dy over dx is really take the derivative of the outside, which is t to the fourth, so dy over dt, times the derivative of the inside, and the derivative of the inside is going to be dt over dx, and that's going to give me dy over dx. So we're just using the chain rule, but here we're actually kind of writing everything out. Now, since we're doing partial derivatives, you're going to see the partial sign, and since we're taking the actual derivative of some function, you'll see the d's in there as well. All right, so for functions of more than one variable, the chain rule has several versions. The first version deals with the case where z is equal to f of x, y, and each case of the variables x and y is the function of a variable t. This means that z is indirectly a function of t. Z is equal to f of g of t, h of t, and the chain rule gives a formula for differentiating z as a function of t. So, in this case that we have, say we have this function, but x and y are composite functions, meaning they're made up of other variables, and in this case they're made up of t. Even though I have z, x, y, and as variables, and then I have t also as a variable, there's really only one independent variable, and that's t. Right? X and y are dependent upon t, and z is dependent upon x and y. So they're all dependent upon t, so t would be the independent variable. So if we want to take the derivative of this, we're going to really have to take the derivative corresponding to t, because that's the independent variable. And so we do our partial of our function divided by, so right now I'm right here, just so y'all know. So here's the chain rule. All right, if I want to take the derivative of my function with respect to t, then what I have to do is I have to take the partial of the function with respect to x, and then work through x to get to t, plus the partial of f with respect to y, and then work through y to get to t. So taking the derivatives of y and x as well to get to t. So we assume that f is a differentiable function. Recall that this is the case, our partial derivatives have to be continuous in order for us to take our function to be differentiable. So for example 1, the chain rule. We want to find the derivative of our function z with respect to time, or t. So let's go ahead and get started. So the first thing that we do is we'll go ahead and just kind of little write our rule right there. So we need to take the derivative of our function with respect to t. So we have y's and x's, so we'll take the partial of f divided by the partial of x. So no, not divided by, the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times the derivative of y with respect to t. All right, so let's go ahead and take the derivative of our function with respect to x. And so here we have inverse tangent of y over x. And so the derivative of that would be 1 over 1 plus y over x squared times negative y x to the negative 2 power. All right. Now, let's take the derivative of e to the t. I'll just denote that by there. So taking the derivative of e to the t. And the derivative of e to the t is just e to the t. So times e to the t. And now we have plus. And now take the partial with respect to y. So again, we're going to have 1 over 1 plus y over x squared times just x to the negative 1, or 1 over x, and then times our derivative of 1 minus e to the negative t, which is just going to be e to the negative t. And then we'll clean that up, and we are finished. So I'll just write it right here. So now what we can do is we can say y so I can say negative y over, I can multiply that x squared in the denominator, and I get x squared plus y squared times e to the t, so I can put e to the t in the numerator. And then plus, I can multiply the denominators by x, and I can multiply that also e to the negative t. Could go in the denominator, I can keep it in the numerator. I'll just keep it in the numerator. So plus 1 over x plus y squared over x times e to the negative t. And then I can simplify even more. Again, you don't have to simplify this far. Just try to clean up as much as you can without making any mistakes, and you should be all right. And so then I need to multiply the right equation by x to get a common denominator. So I'd have x to the negative t. So x to the times e to the negative t, then minus y e to the t, and now I have a common denominator of x squared plus y squared. And there's the final solution. Let me increase that. All right. Now, for example 2, we're going to use the same logic. We're going to do the chain rule to help us solve this problem. But first, let's go ahead and answer A. So I wrote that down so I don't waste time having to write it down as I'm talking to you. So for 36, reproduction W in a given year depends on the average temperature T and the annual rainfall R. Scientists estimate that the average temperature is rising at a rate of 0.15 degrees Celsius per year, and rainfall is decreasing at a rate of 0.1 centimeters per year. They also estimate that at current production levels, the partial W divided by the partial T is equal to -2, and partial W divided by partial R, and partial W with respect to R is equal to 8. So, First thing is, what is significant of the signs of these partial derivatives? So remember, as we're taking partial derivatives, we're taking them along some axis, and we're taking them along in the going in the positive direction. So when we have the partial derivative with respect to temperature, and if that is negative, as our average temperature rises, it causes a decrease in wheat production. So that's where the negative comes in. All right. Now, the partial of W with respect to R is positive. It means that when a rise in annual rainfall causes an increase in wheat production. Right? So both of those rises correspond to when we take in our partial derivatives, we're going along the axis in a positive direction. All right, now for B, we want to go ahead and estimate the current rate of change of wheat production, dWdt. So now we're looking at some of the values that they gave us. They gave us 2 already. The 2 that they gave us was the partial of wheat with respect to temperature, and then the partial of wheat with respect to rainfall. And what we want to do, if we want to find the derivative or rate of change of wheat production with respect to time, we now have a new independent variable, and that is time. And so what we would do, just to write this out, we'd have the partial of W with respect to, we'll do temperature first. Write that T a little better. Temperature times the derivative of temperature with respect to time plus the partial of wheat with respect to rainfall times the derivative of rainfall with respect to time. All right, so now I'm going to just substitute in. We know our partial with respect to time, and that is -2. Now, what is our average rate of change for temperature? Well, per year, and our average rate is rising at 0.15, so 0.15 degrees Celsius. That's going to be our rate of change for temperature. And then we have the partial of W with respect to R, that's 8, times what is our average change in temperature with respect to rainfall, and that is going to be is decreasing at a rate, so -0.1 centimeters per year. All right, and so now we'll go ahead and do the math. Multiply, we get -1.1. And so here we know that we estimate that the wheat production will decrease at a rate of 1.1 units per year. I'll add that units per year.